Today, we are going to practically observe the properties of homogeneity and additivity in a practical circuit. So, first we will take up the property of additivity.
A system is said to be additive if it satisfies the following condition. For two different signals, say x1t and x2t, if the system generates corresponding outputs, say y1t and y2t respectively, then for the input x1t plus x2t, if the system generates output y1t plus y2t, the system is said to be additive. So here is the schematic diagram of the circuit that we are going to use. Here the signals x1t and x2t are passed through an adder to get an output x1t plus x2t, which is used as an input for the RC circuit. Here the op-amp is used as an adder. Here is the practical circuit. Here the op-amp is used as an adder. The two signals are fed as an input and the output is the addition of the two signals. The output is sent into the RC circuit. Here are the two signals to be added. Both the signals have the same frequency and same phase for easier observation. Now we apply the first signal as an input to the RC circuit. Here we can see that the lower waveform is input to the RC circuit and the upper waveform is output of the RC circuit. We see that the input has an amplitude of 200 millivolt peak to peak and the output has an amplitude of 320 millivolt peak to peak. Now we apply the second signal as input. After applying second signal, we again see that the input has an amplitude of 200 millivolt peak to peak and the output has an amplitude of 320 millivolt peak to peak. Now we'll apply the sum of both the signals as an input to the RC circuit. We see that the input voltage has increased from 200 millivolt to 400 millivolt peak to peak, and again the output voltage has increased from 320 millivolt to 640 millivolt peak to peak. This shows that the RC circuit follows the property of additivity. A system is said to be homogeneous if it satisfies the following condition. For a given signal x of t, if the system generates an output y of t, then for the same signal multiplied through a constant a, the system should generate the same output multiplied through the same constant. That is, for the signal a into x of t, the system should generate the output a into y of t. Let us look at the schematic diagram. Here, a signal x of t is fed into the amplifier and we get a signal a into x of t as an output, which is again fed as an input to the linear RC circuit and hence an output a into y of t is generated. Now this is the practical circuit. Here we use an op-amp as an amplifier and the output of the op-amp is fed into the RC circuit as an input and the output of the RC circuit is the voltage appearing across the capacitor. Now if we look at the oscilloscope, the lower waveform represents the input and the upper waveform represents the output. The input signal has an amplitude of 200 millivolt peak to peak and the output signal has an amplitude of 360 millivolt peak to peak. Now if we increase the input, say to about 400 millivolt peak to peak, we observe that the output has indeed also increased and it has increased to 720 millivolt peak to peak. This shows that the RC circuit follows the property of homogeneity.
Here we have seen the properties of additivity and homogeneity being executed by the RC circuit. But there is a problem. Beyond a further limit, if we try to increase the amplification of a certain signal, the signal is not amplified, rather it is clipped at the edges. This shows that even the amplification circuit deviates from its linearity, not increasing the signal continuously, which brings me to the topic of non-linearity. Actually, everything in this nature is more or less non-linear. Let us look at some of the electrical components which are non-linear. Here are some of the electrical components which the non-linear characteristics, for example diode and the transistor. Here we can see that diode doesn't show linearity at all in any phase, and similarly the transistor has a variety of IV characteristics for different base currents. So now the question arises, why we are spending two courses on linearity when everything around us is actually non-linear? I would like you all to answer this question on the discussion forum, and we'll discuss the need of study of linear systems next week. Thank you.